All right, and welcome to today's webinar, depending on your time zone. So I think we can get started. There seem to be more people joining, but there's also going to be a recording available later. So let's actually just dive in immediately here. So today we're going to talk about basically the intersection of machine learning and databases, especially ArangoDB. So kind of if you want the short TLDR version to decide whether you should stay online or not, this is basically the slide where or the two topics we're going to talk about. Basically, how can multimodel, so the model behind ArangoDB, help us with direct machine learning. So for example, the graph capabilities or the natural language capabilities from Arango search. And then the second part is how can also databases help us for like building machine learning infrastructure. So if you want to distinguish that between like target audiences, the first is probably more targeted towards like a data scientist dealing directly with the data, whereas the second also is really crucial for a data ops person who has to manage such pipelines and actually build a production grade machine learning pipeline. So as we're here and with ArangoDB, this is basically what we coined as the ArangoML initiative. And so we're going to see that a little bit in the context of ArangoDB, but most of that is actually pretty specific and relevant to any machine learning system you plan to build. Who am I? I'm Jörg. I'm the head of engineering and machine learning at ArangoDB. Prior to that, I actually built a lot of different machine learning pipelines at different companies, especially in finance and the healthcare space. Was over at Mesosphere, at Suki. And prior to that, I was, again, already in the database field. So I kind of been switching back and forth between big, large-scale infrastructure and databases. And so I'm really happy that I can combine both those passions right now here at ArangoDB. All right, so maybe just as kind of like a quick primer, why is machine learning relevant, or why is it becoming so popular nowadays? I mean, our data scientists sitting in front of their laptop with TensorFlow, they actually have all the tools at their hand to become like a superhero. And this is mostly due to three different factors. First of all, in today's world, we have enough data available to actually train neural networks from scratch, or also besides neural networks, a lot of other different machine learning frameworks. So just the amount and quality of data available is one of the big factors here. The second is probably that we just have enough compute capabilities available. So anyone can go to Google Cloud, AWS, and get like large machines, and especially also get like specialized hardware such as GPUs or even TPUs in Google Cloud for machine learning. And the third factor is also that research actually has made huge labs, especially if it comes to like deep neural networks. So those are basically the tools turning like our data scientist into the superhero figure here. And this superhero can build a lot of cool stuff. So we probably all heard about like self-driving cars, like Teslas being able to drive mostly autonomous on highways. Then there is a lot of other cool networks, such as, for example, DeepBach. That's a deep neural network which can actually compose music, which for me is pretty indistinguishable from original Bach music. So that's really impressive to see, or in this case, hear. If we imagine like the normal life of a data scientist, and this is actually what I've seen in most also even big enterprises, they start hiring data scientists, and this is kind of the process or the outcome they expect to happen. Data scientist is sitting there, he can focus on writing this cool machine learning code like DeepBach, or like an algorithm, create a deep neural network for self-driving cars. So he's just writing that, he's training that model once, and that's going to give us a really cool model. And then we can actually just give him like the next problem to solve. Unfortunately, in reality, the picture is very different. So in reality, and this is taken from a paper by Google, so probably they're already pretty advanced compared to most other companies, but the part where a data scientist is actually writing ML code is only the small black box in the middle. All the other parts around are kind of data verification, feature extraction, is where he is actually spending most of his time. And this is probably like the biggest lesson. So if you only want to take one lesson from this webinar, is that building the entire machine learning infrastructure is a pretty hard task. And so this is why many big companies, after those initial failures where they just wanted to start out with this one superhero in the middle, they actually get side gigs or kind of like helpers for this superhero, because by himself, him or herself, he cannot be super efficient. And the probably most important one here is the data ops engineer. And this guy is combining two different skills. First of all, it's data science and distributed systems engineering. So he's understanding enough to understand this data science world, but on the other hand, he also understands what it means to deploy large-scale distributed systems, hopefully some experience with Kafka, Cassandra, HDFS, and basically understands more the computer science side of things. A lot of the data scientists more come from like a mathematical background and are really great at modeling different data models, but they are not so well versed on the side if it comes to computer science parts, especially like large scale distributed system. So this is why those data ops are basically like the DevOps for data science, and they help to actually set up the entire infrastructure and also best practices around that. And I'm sorry for kind of like the he-she debate. It's kind of like the superheroes, most of them seem to be male as of now. So, okay, how does this picture then look like if we can actually divide the work? With that, the data scientist can actually focus on like wrangling data. So feature extraction, writing the machine learning code, and analyzing the models in the end. Whereas the other labor is taken over by both the data ops engineer and more traditional like DevOps or sysadmins, setting up the entire normal infrastructure surrounding that. And so with that, we typically end up building an entire machine learning pipeline. So machine learning pipeline, it goes from like the raw data sets, which can be stored in either databases, HDFS, or it can also be streaming data coming in through like a Kafka pipeline. Then, and this is probably still where the data scientist is spending most of his time, comes the part of feature engineering. So this is data preparation and like analysis, and basically wrangling the data in a format that it can be consumed and is usable for a deep neural network or your favorite machine learning framework such as TensorFlow, Spark, PyTorch, MXNet, or what else you want to use. And this step, feature engineering, typically involves data cleaning, so getting everything in the same format, considering, for example, miles versus kilometers, getting rid of unknown entries. So if there are like empty entries, I want to harmonize that. And then also just extracting like usable features. So for example, if my initial data set is a graph, typically I want to extract something more in like a row or column format, because by now, still as of today, this is the default format being taken in by, for example, TensorFlow. So if you look at TensorFlow records, which is the input format for TensorFlow, this is closely following like a row structured format. So if I have differently shaped input data, I kind of have to harmonize it over there. And this comes down to feature engineering. Another example of feature engineering is, for example, create a user representation. So if I have my huge data set on the one hand, but I want some representation of a user, I would, the first data scientist would kind of create this user representation, and that would be a feature, and that can also be used by other teams later on. Then comes the actual model training part, typically involving a large number of compute resources and our favorite machine learning frameworks. And then after that, actually the output of such training run is typically not just a single model, but we actually end up with like a range of different models for different hyperparameters, maybe also for different model functions. So a typical machine learning pipeline is not building like a single model we want to deploy later on, but we actually have a bunch of models to keep track of, and from which we then have to choose which one to deploy into model serving. Model serving is basically the term for like put it into production and expose it to live real data sets. Examples of such pipelines are, for example, TensorFlow Extended, or short TFX. So this is the pipeline around the probably well-known framework TensorFlow. And especially now with the release TensorFlow 2.0, it's become pretty prominent and allows us to build such kind of pipelines. And so, for example, the original TensorFlow part, which most of us, if we start like with this 101 TensorFlow example, is the trainer part with like our Keras code. And all the other stuff around is covering the other parts of our pipeline. The other one is probably Kubeflow. So Kubeflow originally was designed to kind of run TensorFlow on Kubernetes. And now there are also like a large number of different projects in that ecosystem, for example, for model serving or similar stuff. Okay, so how do databases play into this? Probably if we have dealt a little bit with machine learning, it's kind of obvious that on the data side, databases are a pretty powerful tool. And data is also one of the most important factors if I want to build a successful machine learning pipeline, and especially taking care of data quality here. So this is probably the most obvious part where we would expect databases. Second part is in this feature engineering step. And here we're especially interested in the kind of query capabilities or processing capabilities of databases. And let's take a look. So for example, if we Google for graphs and machine learning, we're getting a lot of results right now. So this is also a pretty hot topic in both industry and also research. And one example of what we often end up doing is how can we, for example, turn a graph into something which we can feed into TensorFlow. And so one example here, we have like the movie example. If you have ever dealt with ArangoDB and tried out one of the examples, probably you've dealt with this movie graph. And one feature we could, for example, extract from this graph is like the number of movies made by each director. There are a lot of other examples. So for example, I can also do some clustering, try to find out where are communities in the subgraph, and then use those communities as input to a neural network. Other related feature engineering tools might be, for example, shortest path queries, where I want to find out like which things are related. And I can even build like product recommendations. If you look at stuff which, for example, Amazon or other product recommendations engines are doing, is those are basically graph queries, which I can then turn into features being fed into a neural network. And so that could, for example, look like I'm using a raw data set. This can be my graphs, this can be documents. And then I can leverage, for example, ArangoDB, something which we've seen with some people. What's a use for that as well is, for example, Arango Search, where you can extract from a full text certain features. So for example, finding all movies, if we go back to our movie graph example, finding from all the movie plots, all the movies which mention Batman and Robin or something like that. And this gets turned into a feature which can then be consumed by, for example, TensorFlow, MXNet, or another machine learning framework. ArangoDB, if you're actually new to ArangoDB, is a native multimodel database. And this actually means it can store key value, documents, and graph in its native form, but still within the same database engine. So in real life, I mean, there's, for example, MongoDB, there's Neo4j being a pure document / a pure graph database. But in most real life use cases I encountered, it's not like a pure graph use case or a pure document use case. So what I've seen a lot of people do is implement in a layer on top where you can merge data from both a graph database and a document database. And the idea behind ArangoDB is really to put it into one database core. It's also distributed, so even your graphs can span multiple nodes, and there's like one query language across all those different models. So yeah, as mentioned, this is kind of the multi-model idea where on the one hand, I can store all those different formats in its native form, so JSON document, graphs, and key values. And on the other hand, I have the query capabilities to actually query across all of those. So I can natively issue graph queries, graph traversals. I can utilize Arango search to analyze full text search, and I can also dive into JSON documents. So for me, multi-model is kind of like this one thing, like actually being able to store the data model, but probably more important, especially for this feature engineering part, is to be able to query and process different data models in a native, easy way. If we are talking about features, another important or a very powerful tool is to have a so-called feature catalog, or also called a feature store in some systems. And as mentioned, probably 60, 70, 80% of your data scientist's time will be spent on this feature engineering, extracting features. So actually being able to reuse them is a pretty powerful and accelerating tool, because if the second data scientist comes in and is needing this user feature, the first one has already delivered, he can just look at the feature catalog and actually reuse that. So he doesn't have to come up with that from scratch. He doesn't have to do all the data cleaning. He doesn't have to figure out which feature representation works best for him. And there are actually multiple open source implementations. So there's, for example, Uber, Michelangelo. Airbnb also has their own one, but that's not open source. Logical Clocks, a startup from Sweden, also has their own feature store. And in Kubeflow, there's also a project called Feast, being a feature store. If you're interested in building machine learning infrastructure or such machine learning pipelines, I would also recommend the papers around Uber's Michelangelo, because they've been pretty open in sharing a lot of that, their best practices. They also donated a system called Horrorwood for running TensorFlow in a distributed setup very efficiently to open source. So there's a lot of great lessons to be learned from those papers and their blog posts surrounding Michelangelo. I think I'm just going to skip that. The probably next step in, if we talk about graphs and machine learning, is to talk about graph neural networks. So this is the idea of using graphs directly as input to neural networks, or also as outputs. And then, for example, predict edges, predict node labels. And this is currently active research, but I believe it's pretty powerful, because for us humans, it's a very natural thing to actually think in relationships, which can be expressed as a graph linking different entities. And so if we can just feed that into a neural network directly, we don't have to do that feature engineering part. We can basically feed in a representation of the network directly. And the network can just figure out what are the best features by itself. So I'm basically getting rid of this pre-processing step, and the network can directly leverage the graph structure. So the next step where we can also leverage databases is actually to manage the entire metadata for this pipeline we are seeing here. So far, we only talked about data which is directly being used for machine learning itself, but equally important it is to talk about metadata. And let's see what we actually mean by metadata. So in those jobs where we build machine learning pipelines, especially in finance and healthcare, a common challenge were audit requirements. So for example, tracking the lineage across, like, this model has been derived from this data set, this feature has been involved, this Jupyter notebook, this experiment/training run, and so on and so on. So for example, to give one example, in healthcare space, we were dealing with patient records. And under GDPR, it's kind of unclear whether a model being trained with GDPR relevant data, i.e. patient data in our case, actually also makes the model itself GDPR relevant. So we at least wanted to be able to trace which patient data ended up in which machine learning model, because if a patient was retracting his consent for us to use that data, we at least wanted to be able to identify that model, and then in a second decision whether we have to pull it or not. There's a really interesting paper about how such individual records can actually be exposed by a model. So this is like the secret sharer, and it's a really interesting read to understand how information like, for example, credit card data could trickle through an entire pipeline and be exposed through that model. And our main challenge in being able to trace that, which patient record ended up in which model, or which model was impacted by which patient record, was that each of those systems, each of those steps, like the data storage, the feature engineering part, the model training part, model management, and model serving part, was having its own metadata. So what we actually had to do to trace that through this entire pipeline was to go into like 5 to 6 different systems, and then basically doing a manual join across all those data sets. And obviously this was pretty hard and pretty labor intensive. We had similar requirements in finance, where we just needed to have an audit trail to be able to explain how this model was trained. So here are some other use cases, like understand the complete provenance of a model, very important for auditing, and understand the version history. And once we had that, this was, as said, mostly driven from this audit perspective. But once we had that in place, that we could answer such queries, it also became obvious that it was super useful for other stuff as well. For example, comparing performances of similar models being trained from the same data set, being trained with the same model function. Identify reusable steps where I don't have to retrain a model, or I can leverage and use transfer learning to further train a model. And then also to detect, for example, data shift. So data shift is if your training data has a different distribution, and then over time, certain characteristics of your data change. And hence your model, which you trained with that original distribution, is actually not applicable to that incoming distribution anymore. So it actually turned out that having a common metadata layer, which we ended up implementing, was a super powerful tool to answer all those queries. And it also made the data scientist's life actually much easier, as I could easily figure out this Jupyter notebook, if I want to work on that model being deployed there, I have to improve that. This is a Jupyter notebook to start with, because they only had to query like one system, and they didn't have to do a join across different data stores here. So as mentioned, like metadata, what do we all mean by metadata? So with metadata, we don't mean the data sets itself, we don't mean the models itself or the artifacts itself, but it means information about them. Where's the data set stored? What is the training performance for a particular run, for a particular experiment? Where's my model in the end stored? So basically kind of the description or index, being able to look up the data. And so here, just some example, like a data set description, the transformation description, turning that into a feature. Where's a feature representation stored? So I could, for example, reuse that directly without having to touch the original data set again. Descriptions about my notebooks, and so on and so on. And this is exactly the idea for ArangoML Pipeline. So ArangoML Pipeline is an open source project, and it's a common extensible metadata layer for machine learning pipelines. So it's basically this one common metadata store, but it's extensible. So I'm not forced into a fixed schema, as we will see on the next slide, as we have seen that different people are going to build slightly or more or less slightly different machine learning pipelines. So I personally believe having a fixed schema probably won't help you too much. And this is actually where we started looking at ArangoDB, and or more concrete, the multimodel idea behind ArangoDB. And this is pretty suitable here because each individual entity, so for example, the one experiment and the training statistics, like the training accuracy, this actually fits nicely into a JSON document because, again, we don't have a fixed schema. The training statistics for an MXNet run look different from a TensorFlow run, but we still can kind of fit that in this document structure. On the other hand, we kind of have to keep track of the structure between those different entities. So if I have the metadata for describing an experiment with the training statistics, with the test statistics, I need to be able to figure out from which feature was that derived, which feature was actually going into this experiment, also which feature version, which transformation have led to this feature, and then which data has led there. So basically, I need a way to create that graph connecting those different entities. And this, again, is exactly the idea behind multimodel, that I can combine the unstructured data, which I want to store in a document store, in JSON documents, and then create the structure in between them, the connections in between them, using a graph. And using such model, this question, which models are impacted by which data set, actually just becomes a graph traversal. So it becomes a really expressible query, whereas otherwise we would have to do like manual joins across this entire pipeline. And also keep in mind, like a model might be derived from another model using transfer learning, or also features might actually be based upon other features. So we might have like loops in here, which make it even harder to figure out which models in the end are all impacted by this one data set. Yeah, and as mentioned, like a lot of queries across this can easily be expressed by graph traversals then in the end. ArangoML Schema. I put schema in quotation marks simply because there isn't a fixed schema. We kind of have default entity types describing, for example, a data set, describing a transformation, which are kind of like more first-class citizens in UI and other queries. But nothing stops you from creating your own type here. So if your machine learning pipeline actually requires a totally different entity type or has different connections. So for example, you're not using Jupyter notebooks and you want to go from like features directly to model functions, there's nothing forcing you to actually implement this schema, but this is kind of the default schema to give you something to start with. But again, using having a graph database where you can define your own connections makes this really extensible, because you can target that to your own machine learning pipeline graph. And then there's a UI involved. This is still pretty much under development, but this UI basically allows you to search for metadata. So either you're a data scientist, they're able to look up data sets, they're able to look up what's currently deployed, and then also the associated metadata. So for example, if I'm starting from an experiment, I can easily look up which are related deployments, which are related feature sets. So I can basically just look at the entire graph for each individual entity. And so I can figure out visually even what is all related to this one entity, and hence explore the graph structure connected to that. All right. So the APIs, first of all, and this is probably where most people will start with, it's a Python package I can leverage from my Jupyter notebook. I can leverage from my code. And again, this is, it doesn't matter whether I use Scikit, whether I use MXNet or another machine learning framework, because it's a simple Python package here. We also have an HTTP API, which I can leverage directly. So I don't even have to use Python code if I'm in a different environment. And we are also working on the direct TensorFlow extended integration. So TensorFlow extended has its own metadata store, MLMD, which is pretty specific to the TensorFlow pipeline. And it's also, to be honest, the interface isn't that easy to use because it's gRPC based. And so actually writing that was a bit tedious, but in the end, you can just imagine ArangoDB being another database down here. So if you want to use TFX as your platform of choice, you actually don't have to do any manual calls. You don't have to use a Python library. It just gets written into that database directly. The other project, which is, as you can see here in its alpha version, but we're currently talking to them where it makes sense to integrate, is Kubeflow metadata. And so this is basically for this Kubeflow pipeline we mentioned earlier, where they are also currently looking into this problem of metadata. So for us, this isn't really competition right now. I wouldn't see it as that, but it's more like a validation that it's actually a real problem we should look at. I'll jump into a quick demo. So I believe we still have some time left. Yes. But otherwise, already here is the links if you want to look at to ArangoML. So we have demos. All of our demos are basically Jupyter notebooks you can easily run yourself. So if you just click through here, this is all either in the slides or also in the GitHub repo, you can see how you can utilize the Python API, how to create JSON artifacts for this. Again, is even for TensorFlow if you want to kind of do it manually. And so once you've done that, we can take a short look at the UI. So we can find all our deployments. We can look at our data sets. And we can, for example, look up which models are related to this data set. And once we've done that, we can also simply look at the associated graph. The next version, hopefully I'll be able to even click all of those. This is kind of like our goal for the next version. So I kind of can keep exploring that graph for specific deployment. But this already is a pretty powerful tool for data scientists to actually get an overview of the entire pipeline of all entities associated with that. If we look at how that's being stored in ArangoDB itself, if you're familiar with ArangoDB, those two different collections. So collections are kind of like some table abstraction for a multi-model database, especially ArangoDB. On the one hand, we got collections describing, for example, here are our data sets, so our source, text, versions. And then on the other hand, we got the edge collections connecting them. So for example, here with data set, we have our edges connecting a data set to a feature set. And those can actually be also arbitrary connections. So as said, this is kind of our default schema, but it also extends easily to your own structure, to your own machine learning infrastructure, as we are not bound to this particular schema. All right, having that said, thank you so much for listening. I'm more than happy to actually take questions and feedback. So we are interested in what kind of challenges are you seeing with your machine learning infrastructure on the one hand, or for example, also what other graph or machine learning capabilities would you wish for in ArangoDB itself? So this would be super helpful feedback to actually also drive the roadmap for the next ArangoDB releases. So feel free to just ask questions in the chat, and let me have a look whether there are any already. Otherwise, there's also a Slack channel. If you're in the ArangoDB community Slack, just check out the ArangoML channel, and you hopefully get an answer soon. Okay, then thank you so much for listening. And hopefully this was useful. Feel free to ping me afterwards if you have any follow-up questions, or whether you think of using this. More than happy to help you leverage that in production scenarios. Thanks.